Namaskaram. Now a quick recap of the situation as we have it so far. If you want a more detailed breakup of the entire experiment, check out the previous lesson where we introduced the basic experiment. What we have here, just a quick recap, is our car. Sorry for my weird diagram. Our car is on the straight road. As we remember from last time, we are measuring the time elapsed during its travel using the letter X. So X is the time elapsed from the start. The start is when we kept our stopwatch at 0 seconds. So time elapsed from X equal to 0 seconds, that was the start. And as the time elapsed, the car kept traveling on the straight road, and at different points in its journey, we could measure its distance that it has traveled again from the start. The distance is represented using the letter Y. Distance traveled from the start. The start is again measured from here. So the distance is always measured from here, and the starting position for the distance again, just like the time, is now Y equal to 0 meters. So X equal to 0 seconds, Y equal to 0 meter. From here we measure both passing time as well as the distance traveled by the car. And while it's doing so, it's maintaining a constant speed of 5 meter every second. Now, this whole story, if you remember from the previous video, we were able to encapsulate it and make it into what we call as a mathematical model. And the simplest form of mathematical model is an equation. And this is what we landed up with at the end of the first lesson. Y is equal to 5x. And this was perfectly great. Now, where we left off last time was we had this equation y equal to 5x. Now, we want to continue to simplify our lives and try to find out a pictorial way, a visual way of representing this equation. Basically, we want a picture of this equation y equal to 5x, and that brings us to where we are now. So now how do we represent our equation y equal to 5x as a picture? Let's take it in parts. Let's start with our quantity x, which is basically the time elapsed. Let's see how we can represent passing time on a space like this as a diagram. The easiest way to do that will be, well, time is passing. So the best way is represent passing time like a straight line, right? So all that we do is exactly that. We'll start from x equal to 0, that is time equal to 0 seconds, the start of the experiment. And as time is passing, we can think of it as a line that I will draw on my picture. A straight line showing me the passing of time. This is where the term timeline comes. Now, we are quite familiar with the term timeline thanks to Facebook and Insta and all that cool stuff, right? What is the idea of a timeline? You are representing time, something that you really can't see. You're representing it in a way that you can see it. You're representing it as a straight line. Passing time, we call it timeline. Now, a more mathematically precise term for something like this is we're representing something along one direction. Without changing the direction, we're representing that. Sometimes we use the term axis for that. Now, the term axis has a couple of different meanings in different situations in mathematics and science. But generally what it means is one basic direction along which something is being shown. That's generally the idea. So this is our time axis. And of course, in our experiment, since time is represented using the letter X, another way of saying the same thing for our timeline, you can call it the x-axis. So when you see x-axis, it simply means you're taking a given quantity, in this case, in this experiment, time, and representing it along one fixed line or one fixed direction in your picture. Since you call time by the letter X, that direction is called axis, or that line is called axis. Now we call it x-axis. Don't be too fussed about the letters. That's pretty much up to you. We're just using what we generally use, right? And how do I represent it right now? I've labeled it here, time. The unit of time in my experiment is seconds, and the arrow just shows that this can continue. I've stopped at 5, but you can keep going for however long you need. Now, very importantly, the specifics of how we do this representation. Now, we're representing time along our x-axis. Now, we also need to know, okay, once I'm doing this, how exactly is the quantity of time represented? What I mean by that is now we're calculating time in seconds. So if I'm drawing a timeline in seconds on my diagram, how much of length in this line, how long in this line represents 1 second? or represents 1 unit of time. I'm measuring time in seconds. I'm drawing it as a line. So along this line, how long along this line? Is it 1 centimeter, 2 centimeter, or 5 centimeter? How much along this line represents 1 second? Whatever you want to choose, you can choose, but don't change that once you fix it. In this case, how I have chosen to represent time is every 1 centimeter along this line, I am choosing to represent 1 second on that. So in my diagram, 1 centimeter length along this line represents a time of 1 second. So start from 0, go to 1 centimeter along this line, and that for me is 1 second. From 1 to 2, another 1 centimeter, that's the second. That is second number 1 to second 2, this interval. Then again 1 centimeter, 2 to 3. 1 centimeter, 3 to 4, and so on. So in my diagram, I have chosen to represent along the x-axis, every 1 centimeter is represented as 1 second. Now, this is very similar to how, remember when you were a kid in school, you draw these world maps, for example, right? And in that world map, you have to say, mark out different regions based on the kind of forest cover they have, right? So in certain regions, wherever there is, if that particular region has a lot of forest cover, you will shade it in green. And say, for example, if it's a desert, you will shade that in, say, a color like brown, right? And then at the bottom right of your map, you have something called as a color code or a key or a legend, right? So you can tell the reader, hey, listen, wherever you see green, it means forest. Wherever you see brown, it means desert. This is just like that. This is just to tell the reader how you are representing time along the x-axis. For you, how many centimeter along this line represents 1 second, something like that. It's basically like a legend, so that everything becomes clear. Now, the mathematical term for that legend that we give in our pictorial representation of the equation, we call it scale. We call it scale. Now again, this word scale has many different meanings. In colloquial English, we refer to the term scale to mean the ruler or the meter rule that we use to draw straight lines, right? So colloquially we say, hey, give me the scale. So that is unfortunately the colloquial usage of the word scale, but it's always better to kind of have a situation where a given word has a very fixed meaning and the same word doesn't have multiple meanings. That always gets us into trouble. So when we are referring to scale right now, I mean, they're kind of related, right? Because you're using something to draw straight lines and make measurements. So they're related. But here when we're talking about scale, we're talking about how much we are representing for every passing unit of time. In this case, how many centimeters along my line represents 1 second. So it's just a way of representing a particular quantity on my picture. That's what I mean by the term scale. Now, for the other thing, the geometry equipment that we say, hey, give me your scale, man, I want to draw a line. It's better to use the term ruler or meter rule or simply rule so that we don't get into this kind of a confusion. So now we have our first quantity represented along our picture, the timeline. The x-axis, the scale along my x-axis is 1 centimeter is showing us 1 second. Now, it doesn't look like it's very even right now. That's because of my pretty shabby drawing skills. But here you can just take it right now as every centimeter along this line actually is equal and represents 1 second, even though it doesn't seem like that in my diagram. So our time has now been represented. Now we have to represent our other quantity in our equation, which is the distance traveled y. And we're going to do it in a very similar way to how we represented time. So same way, we're going to represent distance in our picture with a straight line. So distance covered by the car along this path is also going to be represented by a straight line. You can call it the distance line. Like we had our timeline, this is a distance line. This is represented in another direction. I'll come to why this particular direction very soon. But this is basically a straight line representing different distances covered by the car on my diagram. This other direction or this distance line, since distance is represented using the quantity or the letter y, this distance line or this distance direction along which I'm representing distance, I now refer to it as the y axis. So when you see y axis, just like when you saw x axis, you immediately think, okay, when I say y-axis, whatever quantity I'm representing using the letter y, in this case it is distance, I'm representing that distance along another straight line, a fixed direction. In this case, the direction is like this. For the time, the direction was like this. For the distance now, the direction is like this. And this unique direction, this line, I'm calling it as the y-axis. Now, the interesting thing is, both the x-axis, which is in this experiment showing us passing time, and the y-axis, which in this experiment is a line showing us the distance traveled by the car. Both the axes, A-X-E-S, both the axes are starting from the same point. Right? That's very important. The time also, which was going in seconds, the 0 point was here, 0 seconds. And then 1, 2, 3, 4, 5 as time was passing. Same way, for the distance also, the starting value of distance, which was corresponding to the start position of the car, that is 0 meters, where it started from, that point is also the same point on the graph, wherever the time is, right? Wherever the time starts, I've started the distance also from the same point, and then I have 0, then 5 meters, 10 meters, 15, 20, 25, and you can keep going, right? So both my axes, my x and my y, start from the same point. That is, the 0 point for time and the 0 point for distance are one and the same. And this actually basically matches to the start of the experiment, when the car was here, when the time was 0 on the stopwatch and the car was here, so the distance traveled also was 0, right? So since both my axes originate means they come from, what is their starting point? The starting point is here, the same point for time as well as distance. This point is from which everything originates. Originates means from where does it begin. Hence, this particular point where time is 0 seconds and distance is also 0 meters is referred to as the origin, right? The origin of my picture. Now, how do I choose to represent the distance? Just like I needed a scale to represent the quantity on the x-axis, and I chose 1 centimeter along my line to mean 1 second. Same way, I choose an appropriate legend or a scale to represent distance along this line, so that the meaning doesn't change. How much I assign to a fixed level of distance doesn't change throughout my figure. And the scale that I have chosen, just to make sure that the diagram fits in and it's convenient, the scale that we have chosen for the y-axis is 1 centimeter along this line represents 5 meters in the actual experiment, right? So that can sometimes be confusing. What do I mean by saying 1 centimeter equal to 5 meters? I'm not saying 1 centimeter is equal to 5 meters. I am saying in this diagram, on this board, I am showing a distance of 5 meters in the actual experiment by a small line segment of length 1 centimeter. So 1 centimeter is the actual length here, but in my experiment it shows a distance of 5 meters. The next 1 centimeter shows the next distance of 5 meters, so 5 to 10. Then 1 centimeter, 10 to 15, 1 centimeter, 15 to 20, 1 centimeter, 20 to 25. So 1 centimeter is showing a distance of 5 meters in the experiment, so that the diagram becomes small, right? If I made 1 centimeter to actually mean 1 centimeter in the experiment, then the diagram becomes very large, because even for a car to travel 5 meters, I have to draw a 5 meter line now, right? So this makes the diagram nice and snug. So now we have our scale, right, for the x-axis and the y-axis, and now our picture is slowly getting formed. Now, the last point which I alluded to in the beginning, why is it that the x-axis, that is the time, and the y-axis, that is the distance of course is in meter, why have I drawn them at this particular angle, which is shown by this kind of a, like a box kind of a thing, right? Now, if those who are familiar with some mathematics, this angle, mathematically speaking, the angle which is like a T, right? It's kind of like a T or an L, however you want to call it. It's like a T or an L. This angle, if you want to give it a number, in mathematics we say is 90 degrees. Other words to represent how one line is at 90 degree to another line is we use the term perpendicular. We use the term normal. Now when I say normal in mathematics, I don't mean normal, abnormal. I mean when a line is at 90 degree to another line, or when a line is perpendicular to another line, we can say a line is normal to the other line. So the word normal also refers to being at 90 degrees, forming that T or L or whatever you want to call it, right? Another word for that is orthogonal or orthogonal, however you want to say it. But basically the point is this line and this line make this 90 degree or T or L kind of an angle. Why is it? Why is it that I have put it like this? Why have I not put the y-axis like that, right? At maybe like a 45 or 30 degree angle. What is so special about this? That is the game changer here, and this is something that's often not really explained in great detail. I want you to look at this diagram and imagine you're standing at our origin at the start. The beauty of this 90 degree angle is that, see, in life, whenever too many things are changing, right? And this is true for life, math, science and everything. Whenever too many quantities are changing, there's too much happening, right? So what is our first instinct? Our first instinct is, wait a minute, too many things are changing. Let's ignore all the other changes. Let's look at the first thing. Let's look at one quantity that's changing. Let's tackle one problem at a time. Let's somehow keep all the others fixed. Let's not change other things. Let's handle this problem, study it, figure it out. Then, okay, once we figure this out, we'll hold this, we'll fix this, and then we'll try to solve others, right? So we're always trying to make our lives simpler by attending to one problem at a time, while somehow not changing other situations in our life, kind of keeping them temporarily on hold until we can come and address them. In math and science, it's always the same thing. Our life is always revolving around reducing the number of things that are changing, reducing the number of variables, right? So that we can attend to one thing at a time, keeping the others fixed. Then once this is done, sort it out, put a pin on it, then go to the other one while keeping this fixed. And then after that, we can combine them and see how they all happen when everything is changing, right? So our idea is to study one thing at a time without the other one changing, just for the purposes of understanding it, right? And that is where this 90 degree becomes a game changer, to reduce the variables that we have to study. Now I want you to go back to this origin. Imagine you're standing here, right? Now, imagine you start taking a walk and you walk along the x-axis. You walk along the time axis. Now, as you walk along the x-axis, what happens? The distance that you have moved away from the origin in this direction keeps on changing. It keeps increasing as you move further and further away. Just if you're just taking a walk along the x-axis, right? So as you take a walk along the x-axis, your position in this direction, you can call it right left, the right left direction or the x direction, right? Your position in that direction is changing. But because this y-axis or the distance line is at 90 degrees, one thing very interesting happens. When you walk in this direction, your position in the up-down direction does not change. You don't go up, you don't go down. Your position along the y-axis does not change. That remains fixed. As you can see, keep walking here. You're at 1 second, you're at 2 seconds, you're at 3 seconds, you're standing at the 4 second mark, but you have not gone above and below. As far as the distance is concerned, you're still at the 0 meter distance, right? So when you're moving along this time axis, your position along the y-axis or the distance axis in this case does not change. Only your position along the time is changing, along this direction is changing. The same thing can happen in the other way. Now imagine you're starting at the origin and you move only along the y-axis. You move only along the distance axis. You can go up, you can go down, doesn't matter. Now in that case, if you imagine you're at 5 or at 10 or at 15 or at 20, you have not moved right or left. You have only moved up and down. Your position along the time axis or the x-axis or the right-left direction has not changed. Only your position in the top-down has changed. right? So when you move in this direction, your position in this direction does not change. When you move in this direction, either you can move all along the x-axis or you can move parallel, right? Doesn't matter. When you move in this direction, your position along this direction does not change, right? This is very useful for us, as we'll see why very soon. Because now, when both quantities are changing, because in the actual experiment, as distance is traveling, time is passing, right? So both quantities are changing. So the reality is both quantities are changing. But by showing the quantities like this, I can break down that change, a situation where both are changing. I can break it down into, okay, I'll hold the distance, I'll change the time, then I'll hold the time and change the distance. So the two changes that are happening, change in distance and change in time, I break it down into two steps. First, I will hold the distance and change the time. Then I will hold the time and change the distance, and then I'll eventually get the same result, right? And I can do it in the other order also. I can hold the time and change the distance, and then I can hold the distance and change the time. We're not actually stopping time, etc. We're not doing that in real life, right? What's happening in real life is both are changing. But while doing it in this way, we can attend to, or we can pay attention to one change at a time, and then in the end put them together and see the overall effect, right? That is where it's crucial that in any picture that we form for an equation, the angle between the axis or the direction representing one quantity and the axis or the direction representing the other quantity is orthogonal, 90 degrees, perpendicular, normal, all different ways of saying the same thing. Let's make an L or let's make a T. That's the key element here. So now we are ready to actually represent our actual experiment on our picture, just about. Now I've taken a few sample instances in this experiment just as a recap, and then we'll see how we can take this information and put it on our picture, and while doing so take advantage of the fact that our time axis or our x-axis is perpendicular or at 90 degrees to our distance axis, or our, in other words, our y-axis. So let's take a few simple instances, something like that. The experiment starts when the car is in the beginning, where it's not traveled any distance and no time has elapsed. So the initial position is x is equal to 0 seconds, no time, y is equal to 0 meters, has not traveled at all. How have we shown that in our graph? Well, this becomes our origin, meaning where everything starts from, right? And earlier I just put 1, 0. Now I'm going to do a little bit more detail. I put it like this, within brackets 0, 0, right? And you can see why. Because this point is not only the start point for the time axis or the x-axis, it's also the start for the distance axis or the y-axis. So when I put 0, 0, it's basically showing this position. It's showing the start, wherein the first 0 represents x equal to 0 seconds, 0 movement along the x-axis. The second 0 represents y equal to 0 meter. That is 0 movement along the y-axis. No time has elapsed, no distance has been traveled yet. So this point is now the origin, written in the form 0, 0, which means 0 seconds, 0 meters. So we start from there. Now let's take any random point and then see how to represent that on this figure. The random point I have chosen is this guy. That is, after 3 seconds, the car has traveled 5 meters every second. So 5, 5, 5. So after 3 seconds, the car is at the 15 meter mark. If you want the exact diagram, you can check the first lesson. The entire detailed diagram is there. I struggle to draw, so I don't want to draw that whole thing again. So let me say it's somewhere here. I don't know exactly, but it's somewhere here, where the car is now 15 meter away from the start, and our clock reading, our stopwatch is reading that 3 seconds have passed. How do we show this on our figure and take advantage of the fact that our two axes are mutually perpendicular. They're making this 90-degree angle with each other. How does that work to our advantage? Let's take it as a story. Let's start from the start. Let's start from the origin, that is 0, 0. Nothing has happened. Now we have to get to the stage in the experiment where 15-meter distance has been traveled and 3 seconds of time have elapsed. We'll do that in 2 stages. Locking one, changing the other, then locking that and changing the first, as we saw earlier. Let's see how we can do that. Let's start at the origin. And now let us not change the distance. So we are not going to change the movement along the y-axis. Okay, we're just going to take a walk along the x-axis to 1, to 2, to 3 as shown by the arrow here. So now I've walked and I have reached this position, which is the 3-second mark, or I have traveled 3 units along my x-axis. Imagine you're actually walking. Now you're here. Now, if you want to think about what this point represents in the context of the experiment, this point represents 3 seconds have passed, but I have not moved up or down, right? I haven't moved along the y-axis. I've only moved along the x-axis, which means as far as my distance traveled, that is still 0 meters, right? So this point represents, you can think of it as, just like this was 0, 0, this point is 3, 0. 3 along the x, 0 along the y. So this point would be a real point in the experiment if, say, for example, even after 3 seconds the car hadn't moved. Then this point would be a real point in this experiment. But it's not. After 3 seconds the car has moved. We're halfway there. Now by moving here, I've moved to the 3-second mark. I haven't moved the distance. I've locked the movement along the y-axis. But I'm not done yet. Now I'm at this position. Now I've reached the 3-second mark, right? Now I don't want my time to change, right? Because I'm looking to plot the point 15 meter traveled when 3 seconds have elapsed. So now I will lock my movement along the x-axis. So once I reach this point, I'm not going to go any further or back along the x-axis. Now I'm going to move in the perpendicular direction along the y-axis without moving along the x-axis, which means I'm now going to go like this. I can go up or down. Wherever I go up or down here, that will be different distances. But for all those different distances, it will be, the time will be locked at 3 seconds, right? So now I can find out for what distance do I need to go to for the time when the time is 3 seconds. Now I'll see, I'll go up. If I go here, it's 3, 5. But after 3 seconds, it's not at the 5 meter mark. After 3 seconds, it's not at the 10 meter mark. After 3 seconds, it's at the 15 meter mark, and that is my next movement, right? So this position in the experiment, that is 15 meter traveled after 3 seconds, I have now got it in 2 separate ways, in 2 separate steps, where each step involves one movement like this and the other movement like this, maintaining that angle of 90 degrees. So I only change the time, keeping the distance locked. Then I only change the distance, keeping the time locked. And by the combination of this, if both quantities have now changed, and I have got where I need to be, which is the point 3, 15. 3, 15 represents this stage. It represents this, right? Which is 15 meter traveled after 3 seconds. I have done it in 2 very clear steps, right? Now, you could also get this in the other way, right? We could start from the origin, right? Instead of moving along the x-axis, we'll keep our position along the x-axis locked at 0 seconds. We will move along the y-axis to the 15 meter mark. So when I move along this direction, straight up, I am not moving this way. Again, it's an advantage, right? Now I come here. That will take me to this position, shown by the arrow here. Imagine you're physically going there, okay? You're here. This position is actually not a real point in this experiment, because this position implies that at 0 seconds, the car is at the 15 meter mark. But in this experiment, when the time was 0, the car was not at the 15 meter mark. The car was at the 0 meter mark. So this is not an actual point for our experiment, but we're getting there. Now we're here. Now at least I've reached the 15 meter mark, right? Now, this 15 meter mark does not happen at 0 seconds. It does not happen at 1 second. It does not happen at 2 seconds. It happens at 3. So I can now start from here, lock the distance travel, lock the y value at 15 and move only along the x-axis. When I say along, I'm actually moving parallel to the x-axis. I'm moving in the same direction, but not on the x-axis, just a little bit above, little bit shifted above, but I'm still moving in the same direction, right? Now, is it 1? No. Is it 2? No. Is it 3? Yes. So then I move like this, right? So I could have either gone this way, right, making the L or the T like that, or I could have gone distance first and then time, this way and then that way. In both cases, you're still kind of going this way and this way, or this way and this way, right? You're moving like what we call a grid, right? You're moving like a grid. Every movement is at 90 degree or perpendicular to the previous movement. So therefore, every movement, the direction of every movement is in a way such that it does not change your position in the previous direction. If I move in this direction, there's no change in that direction. Then when I move in this direction, there's no change in this direction. So this is called grid-like movement when you're moving in these 90-degree angles, right? Because then it becomes very easy because only one quantity is changing at a time. That's the key here. So I could go this way or I could go this way. Eventually, I am going to reach this position. Therefore, this stage in the experiment is clearly shown. This particular point in the journey is clearly shown. In the same way, in the same grid-like movement, I could show any other point in this experiment by corresponding points over here, and then I can get the picture, which we're going to do very soon in the next lesson. But the idea is the same, right? Perpendicular movements, grid-like movements, right? Locating each point. Now this 3,15 is like the address of this particular stage in this experiment in our picture. So just like that, for every other stage in the experiment, if I follow the same procedure, I'll get an address for each of those stages on my picture in the same way. This is the start of a very, very useful field of mathematics, which we refer to as coordinate geometry or co-geom, right? It is a field of mathematics which helps us using these kind of x-axis, y-axis, this kind of a picture to represent any real life experiment in a very, very clear way, right? Whether it is physical space, whether it is time and distance, whether it is current and voltage, whatever it is, it can be represented in a very, very clear way using this system of locating points in space. This is a branch of mathematics called coordinate geometry, right? Geometry because of space. Why do we use the word coordinate? Coordinate is just a very fancy word to show the location of this particular point by what movements were made. Like 3,15 has been located by moving 3 units along the x-axis. In this case, the x-axis is time. And then we have moved 15 units along the y-axis. In this case, the y-axis is distance, right? So the amount that you have moved along the x-axis is referred to as the x-coordinate. Coordinate simply refers to, it's just a fancy way of saying how much have you moved along that direction from the start, right? So I have moved 3. So in this case, that 3 refers to the x-coordinate. Now, the important thing is the x-coordinate will tell you how much you have moved along the x-axis, right? In this case, that's 3. But actually, what is that? That is how much ever I moved along the x-axis. The actual value is how far I have moved away from the y-axis, right? Movement along the x-axis will take you far away from the y-axis. So the x-coordinate will tell you how far away from the y-axis you have moved. But the actual movement is along the x-axis. That is 3 in this case. Another fancy word for x-coordinate is abscissa. Now, generally we don't use this word too often today, but it's good to keep in mind. Some textbooks, etc. might use it. We call it abscissa. Simply is telling you how much you're moving along the x-axis. Then, how much do you move along the y-axis to locate your final point? 15 in this case, that's called the y coordinate. Again, coordinate simply refers to, okay, how much you're moving, what is the position along the y-axis. X coordinate, position along the x-axis. Y coordinate, position along the y-axis. And again, that weird thing is there, right? If I'm moving 15 along the y-axis or parallel to the y-axis, I'm moving along the y-axis, but I'm moving away from the x-axis, right? So the 15 will tell you that you have moved 15 units along the y-axis. But because of that, you have now moved 15 units away from the x-axis. So remember that. The x coordinate will tell you how much you have moved along the x-axis, which is basically how far you have moved away from the y-axis. The y coordinate will tell you how much you have moved along the y-axis, which basically tells you how far you have moved away from the x-axis. The other fancy word for y coordinate is ordinate, right? So x coordinate abscissa, y coordinate ordinate. Generally, in most mathematical chapters in textbooks, etc., we don't spend too much time on these words. We just say x coordinate and y coordinate. This is where the term coordinates come from. Even today, you know, we're talking about like, give me your GPS location, right? So we say, hey man, what are your coordinates? You know, I am 20 degrees north, 30 degrees east, that kind of stuff, right? That's where, you know, it comes from. It comes from this idea of coordinate geometry, wherein by specifying things like x coordinate and y coordinate, you essentially find out the address of any point, which is a particular stage in the experiment, and you break that address down by saying, okay, you move this much along one direction, hold it, and then move that much along the other direction while holding the first one fixed, right? And that will give you a clear way of locating any point in this region, which is basically any point in this experiment. This is a field of mathematics called coordinate geometry. Now, this entire system of mathematics, the seeds of this was planted by a great mathematician, philosopher, and many other things by the name of René Descartes, right? Sometimes when you read the word in English, you think of it as Descartes, right? But a couple of letters are silent in that word. His name is René Descartes, and he was the first to sort of put forward this kind of system of having, you know, perpendicular axes to locate any point in space, and therefore to be able to represent any experiment and therefore any equation in a very clear way. And these coordinates, like the x coordinate and the y coordinate and this entire system, they are therefore sometimes called as Cartesian coordinates or the Cartesian coordinate system. So when you think of the Cartesian coordinates, or when you think of Cartesian coordinate system, you're basically talking about this, right? One quantity along the x-axis, one quantity along the y-axis, and most importantly, moving in that 90-degree fashion, right? Moving in that grid-like fashion, because that will enable one quantity to be fixed while you change the other. That whole story was first put forward by René Descartes, and therefore this particular system, coordinate geometry, etc., we give thanks to Mr. René Descartes. We call it Cartesian coordinates or the Cartesian coordinate system. Just wrapping up this whole discussion before we get ready to actually plot out the individual points of our experiment. I've just plotted a few more points of this experiment just to show you that whole grid-like idea. For example, we've done the origin already, that's here. The point x equal to 1, y equal to 5. I've done that here. Again, you can move in two ways. You can do the 1 first and then do the 5, or do the 5 first and then do the 1. The location of the point now becomes 1, 5. It's common practice when we specify the location of the point to specify the x coordinate first and then the y coordinate. So when you look at the point, it's also almost like the whole story is told there itself, right? You see the point 1, 5, immediately you know, okay, it's 1 this way and then 5 this way. And in terms of units, the 1 in this case is 1 second, because what quantity we represented along the x is time, and in this case the 5 is 5 meter, because the quantity that we have shown along the y-axis is distance. So this order is generally something that we have fixed by sort of by convention, by agreement, you know, so that there's no confusion. We could have done 5, 1 also. We could have done the y movement first and then the x movement, but just so that we are all in agreement, we generally put it in a way such that we show the x movement first and then the y movement. So we represent it as 1 comma 5. Similarly, the other next point 2 comma 10, 2 seconds 10 meters, 2 comma 10, and of course 3 comma 15. Any other point in between we can represent it in the same way, and that will be the object of the next class, and then we finally get the picture. This class was more about getting the idea of the playground, right? We're just trying to figure out how the axis is drawn, why they're drawn at 90 degrees, just get an idea of how the playground looks, and then the actual plotting of the points is the actual game, which we will do in the next class. And since we always like to specify the address of any point by doing the x coordinate first and then the y coordinate, we always keep that order, right? And that's where we get the term ordered pair, right? The ordered pair simply means it's the address of any point in our Cartesian coordinate space, in our x and y axis space, wherein we first specify the x coordinate and then specify the y coordinate. So we say ordered pair. Pair y because there are two, right? And y ordered because by agreement we've decided to specify the x first and then the y. So we always do it in that order, hence we call it ordered pair. Now we have done the basic groundwork, right? We have set up the stage well to now actually plot the individual points of our experiment, of our given experiment, and then try to find out how the picture looks for this equation. We have not yet got the picture of our equation y equal to 5x. We've just set the stage. Now we begin the game, and that is in our next class. Namaskaram.